Finally, we're going to take a look at the impact of dimensional change on volume. This one's actually a little easier to work on than surface area. So first of all, recall that the formula for volume, in this case a cylinder or a prism, would be base times height. So I'm going to go ahead and calculate the volume first by finding the base, which turns out to be 4 pi, and then finding the volume, substituting in the height, 4 pi times 3, or 12 pi centimeters cubed. Now, if I'm going to double all of the dimensions, that means that the radius is now going to be 4 and the height is 6. So very similar to our surface area problem, except now we're doing volume. So again, I'm still going to need the base, pi r squared, except now that r is 4, I get 16 pi instead of 4 pi. Then, now I'm going to also figure out the volume, substituting in the 16 pi and my new height, which is 6, and I get 96 pi centimeters squared, cubed. So if I look at 12 to 96, how do I get there? I multiply by 8. So when I doubled all 3 dimensions, I had an impact of a multiplier of 8. Now I'm taking a sphere, and I'm increasing it by a factor of 3 on the radius. So same type of problem, except now we're looking at volume, which is, and for spheres, 4/3 pi r cubed. It's on your math chart. And substituting in the 10 inches, I get 4,000 pi over 3 inches cubed. I went ahead and left it an exact value, and you can always go ahead and get decimals on your calculator, and this will still work out the same way. Now I'm going to triple the dimensions. So my new radius is 30 inches. So let's find out what the new volume is. Well, 30 cubed, that's going to be 27,000 times 4 all over 3. Well, 27,000 times 4 is 108,000 over 3 times pi, and since 108,000 is divisible by 3, it simplifies to 36,000 pi inches cubed. Well, it's probably easier for you to go ahead and put this in your calculator, and you will see that the volume increased by a factor of 27. So in some, and then now let's go ahead and look at a rectangular prism. So volume is base times height. 6 times 8 is the base, 48, and then finding the volume including 5, I get 240. Now, this time I'm going to do different changes. This is not proportional change. I'm doubling the height, and in this case, I'm going to say the width is 6. And the length, which is 8, I set the longest side as the length. That's typical. I'm going to leave that one alone. So my new dimensions are 10 by 8 by 18. All right. So my new volume, it's still base times height, but now my base is 8 times 18, or 144. Then volume will be 144 times 10, or 1440. Well, if I take 1440 and divide it by 240, I get 6. So let's take a quick look. When I had all dimensions doubled for volume, the increase was by a factor of 8. When I tripled all dimensions, tripling the radius of a sphere triples all dimensions, the change was a multiplier of 27. Then I doubled the height, tripled the width, and left the length unchanged, and the multiplier was a 6. Well, let me go ahead and use that double. How could I get the 8 from the double? Well, there are 3 dimensions, and I'm doubling all 3. 2 times 2 times 2 equals 8. When I tripled the radius, I went 3 times 3 times 3, which is 27. Doubling the height is 2. Tripling the width is 3. Not changing a dimension, use 1. So 2 times 3 times 1 is 6. So to find the impact on volume, you do not have to go calculate volume at all. All you have to do is apply a product of the factors. Think there are 3 dimensions. And remember, radius for a cylinder or a cone affects 2. Radius for a sphere affects all 3 dimensions. So find the impact on a regular hexagonal pyramid when all the dimensions of the base are doubled and the height is tripled. Well, if I have the base is two-dimensional, so I'm going to do 2 times 2, and the height is tripled, so that's 3. 2 times 2 times 3 is 12. So the volume is multiplied by 12 to get your new volume. Did I actually have to go find any areas or volumes? No. All I have to do is do the factors. You can find the volumes. You're just making your job a lot harder if you go and actually calculate the volumes. So for reflection on this part of the notes, how can you find the effect of dimensional change on volume without calculating the actual volume? We'll use the product of the factors. So if something's doubled, use a 2. If something's tripled, use a 3. If something's unchanged, use a 1. So try to keep in track of how many dimensions there are. Bases are 2 dimensions. Height is 1. When can you use the product of dimensional change factors to make predictions, and when must you do the actual calculations? Well, for the surface area in this case is the one that gets tricky. So that one, unless they all change by the same factor, you're better off doing actual calculations. But for all the other 3D solids, volume works just fine by using the product of factors. Again, and when can you use the product of dimensional change factors to make predictions, and when must you do the actual calculations? That was just on your notes. This is also your essential question, and this is probably a good thing to write a note about in the summary of your notes.